Okay, let's dive right into this explainer. Today, we're exploring the fascinating math behind how matrices can either do absolutely nothing or completely reverse a transformation. You already know matrices are these incredibly powerful tools for reshaping data and space. But right now, we're going to zero in on two very specific, very special types of matrices that are absolutely crucial for everything from basic algebra all the way up to advanced machine learning.
Which brings us to section 1, the do-nothing number. To truly get a handle on this concept, I want you to just think about the number 1 for a second. In a lot of ways, it's the most boring number in all of arithmetic. But paradoxically, that's exactly what makes it so important.
Just look at these super basic equations. 5 times 1 is 5, 7 times 1 is 7. Literally, no matter what you multiply by 1, you get the exact same thing back. In the world of ordinary math, it is the operation that does absolutely nothing. It just leaves your original value perfectly intact.
So, here's the fundamental question that unlocks our entire analysis today. If 1 is the do-nothing number for regular multiplication, what would the do-nothing matrix look like? Is there a matrix you could multiply anything by and just get that exact same data back, completely unchanged?
Well, the short answer is yes. And once you see that, an even more powerful question opens up right behind it. If ordinary numbers have an undo operation, where multiplying 5 by 1/5 brings you right back to 1, can you reverse a matrix transformation completely? Can you literally undo the reshaping of space and snap back to exactly where you started?
Let's jump into section 2, meet the identity matrix. Let's tackle that first question and meet the matrix equivalent of the number 1.
For a standard 2x2 case, the identity matrix looks exactly like this. You've got 1s running straight down that main diagonal from top left to bottom right and 0s everywhere else.
Now, before we actually calculate this, I want you to actively think about it. Based on everything you already know about the row times column rule for matrix multiplication, what's your guess? What happens when you multiply any random matrix A by this identity matrix I?
What's really cool about this result is that every single value comes back completely unchanged. Since we know matrices represent ways of reshaping space, stretching it, rotating it, flipping it, the identity matrix is the one transformation that reshapes nothing at all. Geometrically, it just leaves every point exactly where it already was. So whenever you see the identity matrix pop up in an AI algorithm, just read it as this step changes nothing. It's an elegant mathematical placeholder for doing absolutely nothing to your data.
All right, moving on to section 3, building the matrix inverse. Let's transition to that second, bigger question. We're going to revisit that ordinary number's trick to see how it builds toward reversing those complex transformations.
We know that 5 times 1/5 equals 1. In straightforward terms, 1/5 perfectly undoes the act of multiplying by 5, bringing you right back to that do-nothing state.
And this brings us right to the matrix inverse. If a matrix A represents some transformation reshaping space, its inverse, which we write as A with a little -1 exponent, is the matrix that perfectly undoes it. It takes that transformed, warped space and just snaps it back to exactly where it started.
This brilliantly illustrates the defining relationship for inverses. Apply the transformation A, then apply its inverse, and boom, you land directly back on the identity matrix I. Transformation multiplied by the undo operation equals doing nothing at all. It's the exact same concept as our number example, just scaled up for matrices.
Let's look at section 4, finding an actual inverse. Okay, let's make this concrete and actually compute this undo operation. We'll use a small 2x2 matrix where the values are A equals 2, B equals 1, C equals 1, and D equals 1.
Just intuitively, take a mental pause here. Do you suspect this undo process will be just a simple swap, maybe kind of like taking a matrix transpose, or does it require something entirely new?
Well, it turns out for a 2x2 matrix, there is a very clean, specific formula. Step 1, you take the diagonal values and swap their positions. Step 2, you flip the signs on the other two values. And step 3, you divide the whole thing by a single essential calculation, which is A times D minus B times C.
Let's look at that specific calculation for our matrix. You multiply the main diagonal, 2 times 1, and subtract the product of the other diagonal, 1 times 1. So A times D minus B times C simply equals 1. We divide our modified matrix by 1, which conveniently leaves the numbers exactly as they are. The vital point here is that central number we just divided by. It isn't just random arithmetic. It's famously called the determinant, And if we test our new undo matrix by multiplying it against our original matrix A, it works flawlessly. We successfully land right back on the identity matrix. We found the exact mathematical key to reverse the transformation.
But here is section 5, when undo is impossible. This is a major twist in our explainer. You see, not every matrix transformation actually has an inverse. Sometimes undoing a transformation is quite literally impossible. And understanding why that happens is honestly way more important than just memorizing a formula.
Picture this scenario. Imagine a transformation that squashes all of two-dimensional space, an entire flat plane of data, down onto a single straight line. Every point that used to be spread out is now violently crushed and flattened together onto that one narrow path.
Think about the implications of that for a second. If two completely different starting points both get flattened and end up landing on the exact same spot on that line, could any matrix possibly look at that one squashed point and tell you which of the two original locations it came from?
It can't. Once two different points collapse onto the same location, that spatial information is genuinely destroyed. You can't reconstruct it. Mathematicians call this a singular matrix, meaning it's non-invertible. It throws away information. And beautifully, this perfectly aligns with our math from earlier. When a matrix destroys information like this, that AD minus BC formula we used results exactly in a zero. And as we all know, you can't divide by zero. The math literally stops you from finding an inverse when the information is gone.
Which brings us to section 6, how AI uses inverses. Let's transition here and see how this theoretical math builds into the real world. Where does this actually show up in artificial intelligence?
Let's be precise here, because it's super tempting to overstate things. On one hand, massive deep learning models, the kind behind today's advanced chatbots, are overwhelmingly relying on chained matrix multiplication, not inverses. But on the other hand, classical machine learning absolutely relies on inverses. Techniques like linear regression use something called normal equations, which require inverting a matrix to find the best fitting line. Also, covariance matrices get inverted during pre-processing techniques like whitening, which decorrelates data features. Plus, anytime an engineer asks if a model preserves information or collapses it, they are quietly asking an invertibility question.
So, we know the identity matrix is do nothing, and the inverse is undo, if it's possible. But that single magical number we touched on earlier, the determinant, holds the key to knowing instantly if a matrix safely preserves space or fatally crushes it down into nothing. Just how much power does that one number hold over our data? Well, that is exactly what we'll answer in our next explainer.